Hello learners, today we are going to start with a series of lectures on the laws of motion in physics. In the present part 1, we will be talking about what is force, the effects produced by a force, the types of forces, inertia as a property of the bodies, the law of inertia, the types of inertia, and the examples which illustrate this property. In the earlier lessons, we have attempted to describe the uniform and the accelerated motion of a particle quantitatively. We did not take into account the factors which cause motion to be uniform or non-uniform. In the present chapter, the laws of motion, we will try to find an answer to this basic question. The branches of a tree swing only when the wind blows. The air which surrounds the branches of a tree does not move the branches. It's only the force applied by the wind which swings the branches, or which is capable of changing the state of rest of the branch to the state of motion. Let us suppose we have to move a football at rest. For this, someone must kick it. That is, a force needs to be applied to move the football and to change the state of rest to the state of motion. Let us take another example. Suppose when you left home for school on a particular day, you left some books on your study table as shown. Books on top of the table, in the center of the table. Back home, where do you expect to find the same? Yes, you guessed that right. Suppose back home you find the books disturbed as shown below. You conclude that someone has applied a force to move the books. You could guess this because you already know a property of the objects in nature, that an object at rest always requires a force to come in motion. An object at rest, for example, the branches of a tree which we have discussed earlier, the books or the football, continue to be at rest unless some external agent applies a force to move the object. An object at rest cannot change its state of rest or motion without the help of an external unbalanced force. Let us now roll a ball on a rough surface and observe. The ball comes to rest after covering some distance. Compare the motion of the ball on a cemented floor with that on the rough surface. The ball remains in motion for a longer duration on the cemented floor. The ball remains in motion for a very long time on glass. Why is it so? Let us think. In fact, the smoother the surface, the higher will be the tendency of the ball to continue in motion. We can generalize that for a perfect smooth surface, that is, a surface with zero friction, the ball will continue to be in motion forever. So, the ball in above cases comes to rest due to the force of friction. In absence of an opposing force, the motion will always continue and never come to rest. Even a ball rolling down an inclined plane can be stopped by applying a force against the direction of its motion. Basically, the ball has a tendency to roll down an inclined plane due to the force of gravity. But if we apply a force up the plane, that is an external force to retard the motion, then the motion of the ball can be arrested. An external force is always needed to retard or stop motion. However, it is important to note that no force is required to maintain uniform motion in a body. Every object in the universe tends to oppose a change in its state of rest or uniform motion along a straight path. This property of a body to oppose a change in state of rest or motion is called inertia. Historically speaking, for a very long time, Aristotle's viewpoint about motion, although wrong, was taken to be govern the motion of the objects. According to Aristotelian law, an external force is required to keep a body in motion. Where did Aristotle go wrong? What Aristotle missed was the force of friction. Aristotelian law of motion is flawed and hence no longer of our concern. It was Galileo who contradicted the Aristotelian notion that a force is required to keep a body in motion, and that heavier objects fall faster than the lighter objects under the force of gravity. According to the law of inertia given by Galileo, if no net force acts on an object, the object maintains its state of motion. That is, if it is at rest, it will continue to be at rest. If it is in motion, it will continue to be in uniform motion unless it is compelled by an external unbalanced force. The terms external and unbalanced are very important here, and we will be talking about these words in detail. The above law of inertia was the starting point of Newtonian mechanics. Now let's see and study the laws of motion as given by Newton. Newton built on Galileo's ideas and laid the foundation of mechanics. He gave three laws of motion that go by the name as Newton's laws of motion. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. The first law of motion, as stated by Newton, is every object continues to be in its state of rest or of uniform motion along a straight path unless compelled by some external unbalanced force to act otherwise. This law is known as the law of inertia. The following points are important here. The uniform motion, in fact, implies the motion of a body with zero acceleration. If the net external force on a body is zero, its acceleration is zero. The acceleration can be non-zero if and only if there is a net external force acting on the body. It is to be remembered that all the objects are under the effect of gravitational force. Moreover, for the objects on Earth, the frictional forces also act on an object. Hence, while studying the motion of an object, these forces must be taken into account. Hence, for objects on Earth at rest or in uniform motion, it will be wrong to infer that there are no forces acting on the body. The state of rest or uniform motion of a body implies that the net force acting on the body is zero. The law of inertia thus gives a qualitative definition of force. The force is defined as a push or a pull or a hit which changes or tries to change the state of rest or uniform motion of a body. The objects in universe cannot change their state of motion unless a net force is applied on the body. To bring home this characteristic, let's perform a simple activity. I am going to perform a very simple activity for which I am using a book and this pen cap. I am placing this pen cap on the book, and now I will apply a force on the book from right side. Have a close look at the pen cap. The pen cap falls in the backward direction. Have a look at it again. I am now going to apply a force from the opposite side, that is from left to right. The pen cap again falls in the backward direction. Basically, initially the pen cap and the book both are at rest. When the book suddenly comes in motion, the pen cap, due to its inertia property, tends to remain at rest and therefore falls in the backward direction. Now I am going to perform the same activity in a different manner. I have the rider, the pen and the book. I'll gradually bring them in motion and suddenly stop the book. The rider falls in the forward direction. Have a look at it again, and I am moving now the system towards right and suddenly stop the book. The rider again falls in the forward direction, that is the direction of motion. Initially the system was in motion. When we suddenly stop the book, the rider tends to remain in motion due to inertia of motion and therefore falls in the forward direction. So we can conclude from this activity that objects at rest will continue to be at rest and the object in motion continue to be in uniform motion unless we apply some external force. The tendency of a body to continue in its state of rest or uniform motion along a straight path is called inertia. There are three types of inertia: the inertia of rest, the inertia of motion, and the inertia of direction. Let's take illustrative examples of each type of inertia. Inertia of rest: dusting of a carpet or a hanky or a cloth. What you can do is you can take a cloth with dust particles settled on it, give a sudden jerk to the cloth. Initially the dust and the cloth both are at rest. When we give it a jerk, the cloth comes in motion, but due to inertia the dust particles remain at rest and hence the dust flies off. Example of inertia of motion: when we suddenly apply brakes to a moving bus, the rider or the passengers, they tend to fall in the forward direction. The reason being, initially the bus and the passenger were in motion. When we suddenly apply the brakes, the bus comes to rest, but the passengers continue to be in motion due to inertia and hence they get a forward jerk or they tend to fall forward. We have seen that athletes have to run a certain distance after crossing the finishing line. If they suddenly bring their body to rest, they get hurt because the body has a tendency to continue to be in motion. Hence it's essential that the athlete runs and gradually comes to rest after crossing the finishing line. The third type of inertia is the inertia of direction. That is, a body in motion along a straight path will continue to move along the same path unless a force changes its direction. Here we can take an example. The tangential path of sparks from a grinding wheel is an example of inertia of direction. If we look at the sparks carefully, the sparks move and leave the surface of the grinding wheel along tangent. They do not go along circular path like the grinding wheel. Another very interesting example of inertia of direction is the zigzag path of a hare chased by a dog. Here the hare applies the law of inertia of direction to save himself from the ferocious dogs. In fact, the hare continuously changes his direction following along the zigzag path, whereas the dogs, due to their larger mass and hence larger inertia, fail to follow the path followed by the hare. This helps the hare to escape from the dogs. So the law of inertia finally can be stated as every object in the universe continues to be in state of rest or uniform motion along a straight line unless an external unbalanced force acts on it. Let's talk about the significance of the word external. Supposing you are sitting inside a car and you push a car. You cannot move the car because the force happens to be the internal force. Another example is you can sit on a chair, lift your feet up and try to lift the chair. You will never be able to do it because with your feet not touching the ground, the force which you apply on the chair becomes an internal force and hence you are unable to lift the chair. The internal forces do not alter the state of an object. Similarly, if a force is acting on a body and there is another force from opposite direction which is equal to the earlier force, the two forces formed a balanced system and the net force becomes 0. Hence, the body continues to be in the state of rest or motion and there cannot be any change in state of motion of the body. Let's now introduce a new very relevant and important term, linear momentum. This is a term which measures the quantity of motion contained in a body. Let's explore the factors which affect the quantity of motion contained in a body. Consider the situation shown in the figure below. A heavy vehicle and a bicycle are both moving at a speed of 10 meters per second and they are approaching a red traffic light. Which one of the two, the heavy vehicle or the bicycle, will require larger force to come to rest over the same distance? Which one of the two has larger quantity of motion in it? Obviously, the heavier object, that is the object with larger mass, requires a larger force to come to the rest. The conclusion is larger the mass, more is the quantity of motion contained in the body. Let us consider another case. A ball is thrown towards a player at 10 meters per second. You can see this in the figure below. A force F, small f, has to be applied to stop the ball. The same ball is now thrown at 20 meters per second, that is double the original speed. The force required now to stop the ball over the same distance is now denoted by capital F. In which of the cases can the ball be stopped earlier and easily? Clearly, the ball can be stopped when it is moving at 10 meters per second. That is, smaller the speed, easier will it be to stop the ball. It leads us to the conclusion that a body with more velocity possesses or contains more motion. We have more mass, more motion, more velocity, more motion. Hence, the quantity of motion contained in a body depends directly on the mass as well as velocity of the body. Let us now recall that a helmet is usually required by the batsman facing pace bowlers and not for spinners. This is because a cricket ball from a fast bowler is nastier than the one received from a spinner due to its higher velocity. It is safer to catch a tennis ball thrown at a certain speed than a cricket ball thrown with the same speed. The tennis ball has a smaller mass than the cricket ball and hence it contains lesser motion. The quantity of motion in a body, which is called the momentum, varies directly with the mass as well as the velocity of the body. We can now give a mathematical meaning to the term linear momentum or simply momentum. The momentum is defined as the product of mass and velocity of a body. We write momentum equal to mass into velocity. The linear momentum is generally denoted by P with a arrowhead on top because it is a vector quantity. Mathematically, vector P or the momentum is m into vector v. Remember that it measures the quantity of motion present in a body. We can see that it's a vector quantity along the direction of the velocity. It has both magnitude as well as direction, with magnitude equal to product of mass and velocity, and the direction same as that of velocity. The SI unit of momentum is kg meter per second or kg meter second inverse. The importance of linear momentum lies in the fact that it is related to the force required to bring about a change in the quantity of motion. This correlation will be explored in Newton's second law of motion, which forms the center topic in the next part of the lesson, that is the laws of motion part 2. Thank you.